Thanks for joining me in today's lesson. In this tutorial, we will use the power rule to find the first derivative of a function, and we will write the equation of tangent lines to functions at certain points. So we're in section 13.4b, the equations of tangent lines, and we're going to still be using the idea of limit and derivative. When the directions tell us to use the formal definition of derivative, then I need you to show all of your work and use that formal definition. The slope is equal to the limit as h approaches 0 of f of x plus h, f of x plus h, minus f of x divided by h. That's our formal definition of limit, and we've used this in the previous tutorials to find the slope ultimately. And that was a lot of work, a lot of algebra. Any other time, as long as it doesn't say to use the formal definition of a limit, any other time we can use our shortcut, and it's called the power rule. And obviously it's a whole lot easier and faster because it's called a shortcut. If I'm giving you a function, let's say I've got f of x right here, and I'm looking for the derivative, which is f prime of x. The shortcut, the power rule, says all we need to do is take each term. I've got 1, 2, 3, 4 terms in my function. Do this to each term, take the exponent, multiply it to the coefficient, get 15, and take the degree and drop it down a degree. So x cubed turns into x squared. The next term, negative 4x squared, take the 2, multiply to the negative 4 to get negative 8. X squared drops down a degree to x to the first. Take the next term, the 1 times the 3 becomes a 3. X to the first becomes x to the 0, which basically is a 1. 3 times 1 is just the 3. And then this last term, which is constant, has an x to the 0 variable attached to it. 0 times that coefficient, of course, goes away. And this would be the derivative of our function. F of x is here. F prime of x, the first derivative, is here. And remember, this represents the slope. This is an expression that we can plug a bunch of x values into and figure out the slope along that curve. And remember, this curve, this is a cubic. I'm just going to draw a quick cubic function. This cubic has a different slope at every point. And on the points where the graph is increasing, we have increasing slopes. We have positive slopes, I should say. On the points where the graph is decreasing, because the tangent line would therefore be decreasing, we have negative slopes. And then, of course, when we flip back around to the increasing part, we're back to having positive slopes. And there's a bunch of tangent lines. Where is the slope equal to 0? That happens right here at the top of the curve and right here at the very bottom of the curve. That's where we will have horizontal tangent lines, and therefore the slopes would be 0. So we have infinite points along this curve, infinite slopes along this curve, depending on which point we are. Okay, so today we're going to be writing the equation of these tangent lines to this curve at certain points. I encourage us to use the point-slope form of our equation. So let's remind ourselves what point-slope form is. Point-slope form is y minus y1 equals m times x minus x1. That's our point-slope form. Remind yourselves, of course, that m equals the slope. That's where our slope is going to go in our equation. And the x1, y1 represents the point that we are going through on our curve. So the x-coordinate goes here, the y-coordinate goes here, and the slope goes here, and then we have our equation in point-slope form. I encourage you to use that, and you can leave your final answer in this form. That's fine. Sometimes we might ask you to graph as well, so we'll do that. So that's all the information that you need right now to attack example number 1. So example number 1, let a of x be a function defined by, here it is, here's a of x, x squared minus 2x minus 2. I would like to find an equation of the line that's tangent to a of x at the point when x equals 3. And then I'm going to graph both of them. So if I'm going to be writing the equation of the line in point-slope form, I need two things. I need a point and I need a slope. Let's first talk about the slope, and I'll do that over here. So the slope we're talking about, since we're talking about a of x, we're talking about a prime of x. I'd like to find the first derivative. Nowhere in my directions does it say anything about using the formal definition, so I'm not going to have to do all that work. I can use my power rule. I take the terms of a of x and I do my little power rule. 2 times 1 becomes 2, x squared turns into x, and then 1 times negative 2 turns into negative 2, and x to the first turns into x to the 0. So I have the expression for slope. Now I need to figure out what the actual slope is when x equals 3. So when x equals 3, I'm trying to evaluate a prime of 3. So that's just simply plugging in a 3. 2 times 3 minus 2 will give me my answer. So a prime of 3 is equal to, what is this, 6 minus 2 is 4. And there's my slope. So I have my slope, and I can plug that into the equation. The next thing I need is my point. I need the point when x equals 3 that is on this graph. Well, that's pretty simple. I obviously know the x coordinate is 3. I need to figure out what the y coordinate is. So I'm going to use a of x and plug in a 3. So I just need to find a of 3. Well, that's going to be 3 squared minus 2 times 3 minus 2. I'm literally just finding the output in my function when the input is 3. So a of 3, this is just another name for y, is equal to 9 minus 6, which is 3, minus 2, which is 1. So I know that my point is 3, comma 1. So now we have our point. And if I'm going to be plugging into our point slope form, let's pick a color for this. Y minus y1 equals m times x minus x1. I'm going to be plugging in my y coordinate of 1 right here, so I get y minus 1. I'm going to be plugging in my slope of 4 right here, and I'm going to be plugging my x coordinate of 3 right here, so x minus 3. And there's the equation of our tangent line at the point 3, 1 when x equals 3. Now we need to graph both of these. Well, graphing a line is not too difficult, and I'll do that in a bit. Let's graph this parabola. Let's talk about this parabola. I know it's a parabola because it's a quadratic. It's x squared. So I have y equals x squared minus 2x minus 2. So you could just generate a t-table of values by plugging in whatever you want for x and figuring out the outputs and seeing what the curve is. I'm going to go back to my algebra knowledge, and I know that the vertex, at least when it's written in standard form, I take the x coordinate by finding negative b over 2a. And then whatever I get for that x coordinate, I plug it in to figure out what the y coordinate is. So I know my x coordinate is going to be negative b, opposite of b, since b is negative 2. The opposite of that, of course, is positive 2, divided by 2 times a, and a comes from the first coefficient, so 2 times 1 is 2. So I know that my x coordinate is a 1. So my vertex is going to be 1 comma something. All I need to do is figure out what the y coordinate is. When I plug in my 1 into this function, I get 1 squared, which is 1, minus 2 times 1, so 1 minus 2, which is negative 1, minus 2 more is negative 3. So this is my vertex for my parabola. So I'm going to go to my graph, and I'm going to go to 1, negative 3, and that's my vertex. That's my starting point. The only other thing I really need to look at this point is what is the coefficient of my quadratic term, and since it's a 1, that means it's just my regular pattern. My regular pattern says when I input a 1, I output a 1 squared. When I input a 2, that means go 2 to the right of my starting point, I output a 2 squared, which is 4. Back. When I input a 3, count to 3 to the right, I output a 9, 3 squared. 1, 2, 3, 4, 5, 6, 7, 8. It's just a little bit off. I'll put that right there. And then I know quadratics are exactly symmetrical because when I input negatives, I still output positives. When I input a negative 2, I output a positive 4. And when I input a -3, I output a +9. So this is my nice, smooth, continuous, quadratic. There we go. So there's the quadratic, and now I just need to graph this line. Since this line is in point-slope form, I should be able to know which point it goes through and the slope to get me to all the other points. So the point is clearly right here is 3, 1, or I could read it from the equation 3, 1. So I'm going to go to 3, 1, and lo and behold, that's the point that's being shared by both. And then my slope to get to all the other points, of course, is 4, which means up 4 and right 1. So I'm going to go up 1, 2, 3, 4, and right 1, and here we go. And since I don't have any more space over here, I might go down 4, 1, 2, 3, 4, but left 1. When I connect these 3 points, I can see that I have a nice, perfect tangent line to our quadratic at the point when x equals 3. All right, that's a good looking problem. Go back and watch that if you need to, and let's move on to example 2. So example 2 says let b of x be a function defined by, here's b of x, there it is, ooh, it's a cubic. It says find an equation of the line that's tangent to the graph of b of x at the point where x equals -1. So it's the same thing except we're not going to be graphing in the end. So let's find our slope first. Doesn't really matter. We need to find the slope, we need to find the point, so I'll start with slope. Slope is going to be coming from my derivative, so that's b prime of x. It doesn't say anything about a formal definition, so I can use my little shortcut. So let's figure out what b prime of x is going to be. This first term is going to give me a 12x squared. This second term is going to give me a -5. And this third term is going to wipe away because the 0 exponent will cancel anything away. So there's my expression for slope. I'm not going to underline that because that's not what I want. What I want is the actual number for the slope. And that's what's going to happen when x equals -1. Once I know what b prime of x is, now I want to figure out what b prime of -1 is equal to. So this is 12 times -1 squared minus 5. So that is equal to 12, well, that's just 1, that's 12 times 1. I'll go ahead and write that one last step. 12 minus 5, of course, is 7. So there's my slope. So now let's come over here and do the point. We know that b of x, our function, is equal to 4x cubed minus 5x plus 3. That's our function. And I know I'm looking for a point that has an x coordinate of -1. So what I'm interested in now is b of -1. I need 4 times -1 cubed minus 5 times -1 plus 3. Let's see what we get here. -1 cubed makes a -1, and 4 times -1 makes -4. -5 times -1 makes +5, and +3, of course, is +3. And now we've got -4 plus 5 is 1, plus 3 more is 4. So that means that our y coordinate is equal to 4. Remember, b of x, or b of -1, is really just a y value. It's an output. So now I have my point. The x coordinate is -1. The y coordinate is 4. Now that I have my slope and my point, I can plug into point-slope form. Y minus y1 equals m times x minus x1. So I can plug in my y coordinate, which is 4, so this will become y minus 4. My slope is 7, so that comes in as 7. My x coordinate is -1, so x minus -1 turns into x plus 1. And that is an equation of our tangent line. This is an equation that is in point-slope form. If for some reason you did not like the point-slope form and you wanted to get into slope-intercept form, if you wanted to solve for y, then you'd have to distribute right here. So we'd have y minus 4 is equal to 7x plus 7, and then we would have to add 4 to both sides, and we would have y equals 7x plus 11. That's another form of the tangent line. This is the slope-intercept form. Perhaps you like to graph from that form better. That's absolutely fine. I believe it requires a little bit more work, so I'm okay just leaving it like this. All right, great. Let's look at our third example. So example 3 says find the point or points, if there are any, where each function has any horizontal tangent lines. Okay, so this is a little bit interesting. This is different. A horizontal tangent line would look exactly like this. And what we've talked about a horizontal tangent line, at least it's important here, is that the slope would equal 0. So basically, I want to know when is the slope of this function equal to 0. Well, let's first talk about the expression for slope for this function, and that is finding e prime of x, the first derivative. I'm given e of x. It's pretty simple to find e prime of x, at least with our power rule. So our first term turns into 3x squared, our second term turns into 12x, and our third term turns into negative 15. Our fourth term doesn't do anything since it would be 0 times 1. It goes away. So this is the expression for slope. I want to know when is this expression equal to 0? When is the slope equal to 0? Because that will tell me when I have a horizontal line. So I have a quadratic equation. I know how to solve quadratic equations. I'm going to try factoring first. Actually, the first thing I see is in the 3, the 12, and the negative 15, I see a common factor of 3. And since this is an equation, I can simply divide everything by 3 and get rid of that and get my numbers to be a little bit smaller. So x squared plus 4x minus 5 equals to 0. Okay, that's a little bit more manageable. I'm going to try factoring this, so I know it's going to look like two sets of factors. Two sets of parentheses. X times x will be the fronts. There's only one option to get 5. That's 1 times 5. And since it needs to be a negative 5, I know that one of these will have a plus and one of them will have a minus. And I need it to be a positive 4x, so it looks like it's going to be a plus 5 and a minus 1. You can do a quick mental check to make sure that the inner and outer terms do indeed add up to 4x, and I'm pretty confident that that does. So now each of these factors can tell me a different x coordinate. X equals 1, x equals negative 5. So there are 2 points that will have a slope equal to 0. There are 2 points where there will be tangent lines to this curve. One of them has an x-coordinate of 1, the other one has an x-coordinate of negative 5. How am I going to find the entire point? Well, I need to go and plug a 1 into our original function, not into the derivative. If I plug a 1 into the derivative, I should be getting it equal to 0 because we just solved the derivative. I need to plug this 1 into the original function. So I'm going to do e of 1. E of 1 is equal to 1 cubed plus 6 times 1 squared minus 15 times 1 plus 1. So this is equal to 1 plus 1 squared is 1 times 6 is 6 minus 15 plus 1. 1 plus 6 is 7. 7 minus 15 is negative 8. Negative 8 plus 1 is negative 7. So this is 1 point. Let's do the same thing for the negative 5. Again, the negative 5 has to be plugged into the original function. So I'm looking for, let's say I've got negative 5 comma something. Let's do e of negative 5. And that will be negative 5 cubed plus 6 times negative 5 squared minus 15 times negative 5 plus 1. Negative 5 cubed is negative 125. I have to square first to get 25, and 6 times 25 is 150. 6 quarters is $1.50. I've got a negative times a negative, so that's a plus. 15 times 5 is 75, and of course plus 1. So let's see what we have here. Negative 125 plus 150 is 25. 25 plus 75 is 100, plus 1 is 101. So my other point is negative 5, comma 101. So what's kind of neat about this problem is we just found the 2 points without the aid of a calculator. I didn't use a calculator for this. We just found the 2 points where we have horizontal tangent lines, which means we just found a maximum and a minimum for this cubic. I know this cubic generally looks like this. I'll just draw a cubic. And we just found this point -5, 101, way up here where there's a slope of 0, and this point 1, -7, where there's a slope of 0. We just found the turning points for this cubic function. Kind of neat. And our final problem, f of x is 2 over x to the 5th. Same directions. I would like to know, when does this slope equal to 0? First thing, let's find the slope. That's f prime of x. We can use our power rule, but we can't actually use it yet because we don't truly see the exponent because it's hiding in the denominator, and I don't like that. So what I'm going to do is I'm going to bring this x to the 5th up to the numerator, and of course if I'm going to move that, it's going to change its exponent to a negative. We want to see it as a term like this, not as a quotient. So if you have a variable in the denominator, bring it to the numerator and unsimplify it basically, change its exponent to a negative. Now I can take this term and use my power rule. -5 times 2 becomes -10, and x to the -5th drops down a degree to become x to the -6, because -6 is 1 degree less than -5. And then maybe I don't like this, so I'm going to convert this back. The -10, of course, stays where it is, but x to the -6 will go to the denominator to become x to the +6. And this is our derivative. This is our expression for slope. I want to know, when does this expression for slope equal to 0? That's what I want to know. So all I have to do is solve this for x. And what you might first do is multiply by x to the 6th. I see denominators. So if I multiply by x to the 6th and multiply by x to the 6th, I'm going to cancel out that, and I'll have -10. Unfortunately, 0 times anything becomes 0, and then I'm confused. But I shouldn't be confused too long, because this, of course, is not true. And what that means is there are no values of x in this equation such that this -10 divided by x to the 6th would be equal to 0. So there's no solution. And what that means is there are no horizontal tangent lines. So that's kind of an easy problem. There were no solutions to the equation of the slope equal to 0, so therefore there will be no horizontal tangent lines. And let's just look at that graphically to prove. This is a rational function, 2 divided by x to the 5th. There's a vertical asymptote right down the y-axis. There's actually a horizontal asymptote across the x-axis. And I'll just sketch it quickly. This is basically what the curve will look like. You can generate a t-table if you want to. And we can see there are no points on this graph where we are changing from decreasing to increasing or increasing to decreasing. There are no peaks and there are no valleys. So therefore, there are no spots where the tangent line would be 0, have a slope of 0. No horizontal tangent lines. Thanks for watching this tutorial. Go back and watch any of the examples that you might need to, and we'll practice this when we get to class. See ya.